Hey all, so we only have this one lesson this week, so this will give you a chance to catch up on some stuff. You're going to have a short quiz tomorrow if you haven't looked at the calendar already, and then you're going to have a regular work day on Wednesday to do corrections and things like that. So if you have any questions about this schedule, please look at the calendar and then leave any questions remaining in the comments. And then enjoy your long weekend. So we're going to talk about factorials and permutations, and we're looking at homework from 3.4. So get yourself ready for notes, and we're going to get started. So hopefully for several of these ideas, they will feel like review from earlier lessons. We're going to start with just reminding ourselves what a factorial is. So factorial, which is denoted with the exclamation point, is the product of consecutive natural numbers that are less than or equal to that number. So 1 times 2 times 3, n minus 2, n minus 1 times n. So if we're just going to start looking at factorials and how to evaluate them, we're going to start by doing some of them by hand, and then we'll also talk about how to use our calculator for these. So we're going to start evaluating by hand here. 18 minus 7 factorial over 10 factorial times 9 minus 9 factorial. So we'll start by following our order of operations just like we normally would, and this becomes 11 factorial over 10 factorial times 0 factorial. And this is one of the reasons that I wanted to put this problem in here. 0 factorial, contrary to what a lot of students think it should be, is 1. 0 factorial equals 1. And there's a lot of reasons for this. Some of them are going to become apparent in our next lesson where we'll talk about combinations. So we will address this again, but it's important to remember. Then when you're doing a factorial by hand, I recommend that you expand them out. So in this case, you would get 1 times 2 times 3 all the way up times 10 times 11 if we're using this same formula as over here for 11 factorial. And then 1 times 2 times 3 times 9 times 10, and then times 0 factorial, which is 1. And the reason I recommend this is that then you can do a lot of canceling out because it's multiplication and it's fractions. So we're left with this whole big fraction factorial is equal to 11 over 1, or just 11. Now, we're also going to be talking about permutations here. As I said, we'll talk about combinations in our next lesson. And permutations, we have a couple different pieces of notation. We have NPK, or n arrange k, and it's the number of ways to arrange k out of n total elements. If you want to use the formula for it by hand, if I'm looking for that total number of ways to arrange, I'm going to take n factorial over n minus k factorial. Now, if I want to use a calculator, we're going to go to math, and then you're going to go to probability, and then there'll be some number right here, and then it will give you NPR for most part instead of K. It's the same idea, and then you will either have the chance to enter in these numbers when you click enter on your main screen, or you insert them in front, and it's just the number in front of this symbol would be the N, and then the number after would be the R. So let's use permutations as a way to calculate the number of ways that we can have different outcomes. So if I'm looking at number 2, 10 candidates are running for student council president, vice president, and treasurer. How many possible outcomes are there to the election? So this is important because we're talking about ways to arrange, and all 3 of these are different. So if it was a combination, these would all be the same job, and they're just members. So you're going to only have permutations today, but you will eventually be wanting to make sure that you can figure out which is which. So with all these problems, the first thing you want to do is identify what n is and identify what k is. So in this case, we have n is our total number of candidates, so that's 10, and k is we're arranging 3 of them into these 3 positions. Now, if we want to do this by hand, this would be 10 factorial over 10 minus 3 factorial, which is 10 factorial over 7 factorial, which after all that canceling out would be 8, 9, and 10 left, meaning that there are 720 possible outcomes for this election. Obviously, in any election, they are not all equally likely, but those are the entirety of the potential outcomes. Number 3, you deal 5 cards from a standard 52 card deck in a row. How many lineups are there that either consist of all red cards or all clubs? And this is where it's really important, because if you start doing permutations with 52, you're going to end up with a crazy number of answers. And so you want to pay attention to these other parameters. So here we see that we've got 5 cards, so we're arranging 5 things. So this is our K value. Now, we're talking about all red cards or all clubs. So we're not actually interested in the whole 52. For this one, it's n equals 26. And here, n is equal to 13. So there's 13 for every suit in a deck of cards. And since it's or, and there's no overlap, right? Nothing is red and a club. We can just add these together. So this is the same thing as the addition principles from last week. So for this, I am going to use a calculator because I'm going to have 26 arrange 5, which is going to be a very large number. Even if I didn't have a calculator that could do permutations, I would still want a calculator. Plus 13 arrange 5. So use your calculator, plug those in, and we get for the first that there are 7, 8, 9, 3, 6, 0, 0. So we've got 7,893,600 ways to have all red cards, and 154,440 ways for just clubs, which gives us the total of 8,048,040 possible lineups. Now, as I mentioned here, these are really easy to add together because it's either all red or all clubs. There's no overlap. I do want to look at one problem where we are going to have overlap. Number 4, you deal 5 cards out in a row. How many lineups are there that either consist of all red cards or all face cards? So here we have our all red cards, which would be diamonds and hearts. And then the face cards, which are the jacks, the queens, and the kings of any suit. And there's an overlap. There's where we have all red and all face. And you'll notice here, if we zoom in, I've colored in this space twice, right? I've counted it with the red and I've counted it with the face cards. And so this is what we call double counted. So it's counted one too many times. So our total is going to be all the red plus all the face, but then we overcounted that middle section once, so we need to subtract away one count of all red and all face. And this is why Venn diagrams can be really helpful for these sort of things. So all red we've done before. This is 26 arrange 5. All face, there's 3 face cards for every suit, so this would be 3 times 4 for every suit. So 12 arrange 5 minus red and face. Well, there's the jack, the queen, the king of hearts, and the jack, the queen, the king of diamonds. So there's 6 of those. Arrange 5. Again, we're going to do this on a calculator, especially for that first one. The other 2 would be okay to do by hand. And we end up with 7,987,920. So leave me any questions that you have in the comments or emails, or you can set up a Zoom meeting and I'll talk to you all later. Have a great MEA.